Hello everybody. So today we're going to be talking about graphing exponential functions. Now in class today we did an experiment where we saw that the graphs we created from our data were not straight lines. Today in this video what we're going to do is talk about some of the features of these curvy graphs, what they should look like, and how we can describe them. So there are two types of curvy graphs we're going to talk about, and both of these graphs are called exponential. One type is called exponential growth, and the other type is called exponential decay. When the y values of the function are moving farther away from the x-axis, we call this exponential growth. So if we read this graph from the left side to the right side, you can see that the graph is getting farther away from the x-axis. If we have a graph where the y values are moving closer to the x-axis, so if we read this graph from left to right, you can see we're getting closer to the x-axis, then we're going to call that exponential decay. Now, when we talk about these graphs, we talk about three things: the domain and the range and the growth rate. The domain of a function, it describes what x values are allowed to be used in that function. And we can figure out the domain by looking how far to the left the graph will go and how far to the right the graph will go. So in other words, following the x-axis. Now if I look at each of these graphs, because this graph is going to go on forever in the left direction, and it's going to go on forever in the right direction, we would say that the domain for both of these graphs is all real numbers. Range, on the other hand, is talking about the y values. So this is describing how far up and down the graph goes. Because these graphs are not lines, because they're curvy and they kind of flatten out, it means that our range is going to be limited. For example, in this graph, because this graph gets flatter and flatter and closer to the x-axis, the y values of this graph are always going to be bigger than 0. They're always going to be above the x-axis. They're always going to be positive. So we would say that the range here is that the y values are bigger than 0. Now we use a greater than because that means above, and we use a 0 because that means the number that we are above. We are always above 0. Now in this graph, even though the y values are getting closer to 0, they're still always going to be above the 0. So we would still write y is greater than 0 or above the 0, even though the graph is going a different direction. This symbol just means it's always above this line. Now the growth rate talks about whether we are growing or decaying. If we have a growth graph where our graph is getting farther away from the x-axis, then the growth rate will be greater than the number 1. For example, it could be the number 2, 3, or 4. If our graph is getting flatter and it's getting closer to the x-axis, then our growth rate will always be less than 1. So for example, it could be 1/2 or 1/3 or 2/3. Those would all be smaller numbers than 1. Now let's go ahead and look at some graphs. We're going to try to decide whether we have a growth or decay graph and then describe the domain and the range. So in the first graph, I can tell that I have a growth graph because as I go towards the right, it's getting farther away from the x-axis. Now the domain would be describing the x values. Because this graph goes as far as I can see to the left and as far as I can see to the right, this is going to be all real numbers. Now, if I look at the range or the y values, I can tell that this graph is flattening out close to the number -1. So all of the y values in this graph will be above the number -1. So they're all going to be above this number. Now let's look at problem 2. So in problem 2, my graph is going downhill, but it's still getting farther away from the x-axis. So it's going far away, which means we're still going to call this growth, even though it's going downhill. It's getting farther away. The domain would be the x values. Because this graph continues to go to the left forever and ever and continues to go to the right forever and ever, we would say that our domain is all real numbers. And for our y values, our range, well, this time the graph is close to the number 1, but then always below there. So we would say that our y values are always below the number 1. For problem number 3, because this graph is going downhill and getting closer to the x-axis the whole time, we would say that this is decay. The domain would still be all real numbers because the graph never stops. It's going to go really far to the left and really far to the right. The range, however, would be we're getting closer to 0, but we're always above there. So we would say that the y values are always above the 0. So greater than 0. Now let's take a look at making some of these graphs ourselves. So how can we graph an exponential function when we have a set of data? I think what you're going to find is this is very similar to what we did today in class. So if I give you these data tables, how do you graph them? Well, just like we would normally make a graph, we're going to use these ordered pairs. So left 2 up 1/2, left 1 up 1, over 0 up 2, over 1 up 4, and over 2 up 8. Because this is not making a straight line, we know that it must be exponential. So when we draw an exponential graph, I like to say that it looks like an airplane taking off. It's very close to the ground and then it takes off into the sky. Now it's never going to hit the ground. We're getting closer and closer to 0, but it's never going to touch. For problem number 2, we would graph these ordered pairs just like normal. So left 2 up 12, left 1 up 6, 0, 3, 1, 3 halves. Now 3 halves is 1.5 as a decimal. So if it's easier for you to graph it as a decimal, change it to a decimal by dividing. And 3/4 would be 0.75, so a little bit less than the number 1. Now again, it's not a straight line, so it's going to be exponential. I like to say that this graph looks like an airplane landing. So it's getting really close to the ground, but it's never really going to hit the ground, and it's nice and curvy and smooth. Now the second big idea is how do we make these graphs if we don't already have a table? And the answer is we're going to have to make them ourselves. So what we're going to do is fill in these tables using our calculator and making some calculations and then graph those values. So on my calculator, if I plug in 3 parentheses 2 to the -2 power, I get 0.75. I'm literally just typing this in. If I type in 3 parentheses 2 to the -1 power, I get 1.5. 3 parentheses 2 to the 0 power, and I get 3. 3 parentheses 2 to the 1 power, and I get 6. And 3 parentheses 2 to the 2nd power, and I get 12. You're literally just going to type this into your calculator, taking these values and plugging them in, and you're going to get your y values. Then we're going to graph. So left 2 up 0.75, -1, 1.5, 0, 3, 1, 6, and 2, 12. Again, this one's going to look like an airplane taking off. Nice and smooth, and it's never going to hit the ground. It's just going to get really close. For number 2, again, we're just going to type this in. So 2 parentheses 1/4 to the negative 2 power, and I get 32. 2 parentheses 1/4 to the negative 1 power, and I get 8. 2 parentheses 1/4 to the 0 power, and I get 2. 2 parentheses 1/4 to the 1 power, and I get 1/2. And 2 parentheses 1/4 to the second power, and I get 1/8. So if I graph these points, I have left 2 up 32. Well, that's not going to fit on my graph, so I'm just going to skip graphing that point. Left 1 up 8, 0, 2, 1, 1/2, 2, 1/8. Again, this is going to look like an airplane landing. It's going to get really close to the ground but never touch, nice and smooth and connected. All right, that is it. That's the big idea for today. Thank you guys so much for watching. Have a great afternoon, and we will practice this when I see you next time.